Okie dokie. In the last video, we did the first one there. You can still see the answer if you want to go back and recap before we move on to the second one here. Okay, so not much has changed, I would guess. We still have a double bond. We still have HBr, although there should be, let's call it a red flag to start to pay attention to, right? So that carbon right there, what is unique about that? Well, that red carbon is a quaternary carbon. And quaternary carbons are kind of a, hey, pay attention to me, I might be doing an alkyl shift kind of red flag, okay? So you see a quaternary carbon that's next door to our alkene, our double bond there. You know, we need to say, all right, let's see, or let's pay attention as we're going through if we have to do a shift with our carbocation. All right, anyway, let's go back to using green and blue, right? There's our two carbons that are involved with the double bond. Let's start the mechanism off. Alkene swings out, grabs that hydrogen, right? We make a bond to hydrogen, we break a bond to hydrogen. Let's draw what happens after that first step. All right, red. Boy, that's kind of wavy there. Let me draw that a little bit nicer. Green and blue. Okay, so between the green and the blue, right, the two carbons that were involved with the double bond, is one of those more substituted than the other? Is one of those better at handling a positive charge than the other? Right? And the answer is yes. The green one is a secondary carbon. The blue one is primary. Remember, secondary is a more stable carbocation than primary, so we're going to generate the carbocation at the more stable carbon initially between the two that are involved in that double bond. So look at your green versus your blue and say, which one of those is more stable, right? And you find the more stable one and you put your positive charge there, okay? Let's put positive charge. Oh, let's do it in black, just we don't want to get confused with some colors here, okay? So positive charge there on green. We made a bond in orange off of our blue carbon then to our hydrogen that came from the HBr. Got it? Now, I told you guys in the previous video what you always need to do, right? Whenever you generate a carbocation, you need to pause, you need to look, you need to ask the very important question of, can I rearrange this? Right? So I'm looking next door. I look to my right. I see that primary carbon. Am I going to go to the right? Absolutely not. I look to my left and I see a quaternary carbon. We go, wait a minute. I remember that with quaternary carbons, I can do an alkyl shift as long as it is next door to my positive charge. In this case, we've met the criteria. To the left, that red carbon is quaternary, and it's next door to that positive charge. So let's do an alkyl shift. I'm going to zoom in here a little bit just so we can be very clear about what we're doing, okay? So what I'm going to do is I'm going to pick one of those methyl groups, right? One of those methyl groups coming off of that red carbon, and I'm going to shift that entire methyl group over to my green carbon. And my arrow is going to look like this, right? So I'm taking the bond. Let me get another color here. Let me get purple. Purple seems good. Okay, so I am taking the bond between the purple and the red, right? I am taking that bond and moving it to the green. Got it? And remember, when I'm drawing my mechanism arrows, the stuff that I'm drawing in orange, it always goes, the arrows always start from the minus, the electrons, and go to the plus. Never draw your arrow from a plus to a minus. It's always the other way around. So I'm taking that bond between the purple and the red and sending it to the green. All right, so let's draw what happens after that alkyl shift. Okay, so I'm going to draw this a little bit strange, just so we're following along, right? So there's my green, there's my blue, or what blue did I use? I think it was that one. Okay, there's my blue. Okay, there's my red, right? The red was bound to two other methyl groups, the ones that we didn't do anything with. In orange now, right? In orange now, I am bound to my purple carbon, right? So there's my purple carbon there. Now, what am I missing currently? Well, remember, if I took a bond away from my red carbon, that is where my plus is going to be left behind, right? I shifted. So that's what happens color-coded after this step. Now I'm just going to clean this up. Okay, I'm just going to clean this up. Okay, I'm going to clean this up. Let me go back and fill in the colors just so we're all on the same page. And this was blue, right? Yeah. Blue over here. Okay, do you guys see how these two are the same structure? Just one might be a little bit easier to visualize than the other. Okay, it doesn't matter. Right? On the exam, I care about you guys getting the answer right, not necessarily that it's the prettiest looking thing, right? But either one of these would be just fine. Okay, so one is cleaned up. Okay, so we did a shift, we have a carbocation, we asked the very important question, is it at the most stable position? The answer is yes, right? So now we have our plus, our Br is going to be our minus, and so we just wrap things up. Minus goes to the plus. Oops, I meant to draw that in orange just to be consistent, right? Minus goes to the plus. We'll just continue here with our prettier looking cleaned up structure. And there we are. Okie dokie. Okay. I told you guys, remember when we had in the previous video, right, for the first part of this, I said that if we generate or if we have a carbocation, we have to pay attention to racemic mixtures. And fortunately, in this case, we do not generate a chiral carbon, so we don't really have to worry about the whole R versus S thing in this case, right? So what we have there is just fine for answering the questions for what we have at the moment, okay? So let me zoom out so you guys can kind of get a snapshot of the whole thing, right? Remember, this is equivalent to that, right? One is just cleaned versus the other, okay? So hopefully this helps you guys out with walking through our hydrohalogenation mechanisms. Make sure you guys can do this on your own. 100% guaranteed this will show up on your exam. Not necessarily this problem, but this exact same concept, this exact same mechanism.